Hello, I'm Professor John Kelly, and this is the Weber Auto YouTube channel. Today we are going to look at the amazing hybrid transmission used in the Acura MDX and RLX Sport Hybrid vehicles. Now this is a very unique transaxle transmission with the front axle built into it because it has an electric motor built into a 7-speed dual clutch automatic transmission. And so it has all the benefits of a dual clutch transmission, such as quick shifting, but also it has the extra power added by an electric motor. This electric motor is rated at 35 kilowatts or 47 horsepower. And this is just one of 3 motors on the RLX Sport Hybrid. It has 2 more electric motors in the rear drive unit, one for the left rear wheel and one for the right rear wheel, and then combine that with the 3.5 liter engine. It's a high performance hybrid. And so let's take a look at how this thing works, because it's not enough that it's a dual clutch transmission. This is a wet dual clutch transmission. Unlike some other dual clutch transmissions, like this one here that came in the Ford Focus, it had a dual dry clutch transmission. This is a dual wet clutch transmission, and it seems to be a lot more reliable than the dual dry clutch. So there are several things we want to do here. We want to explore the dual clutch features. We want to see how power is transferred through this and we want to see the 3 modes of operation that this transaxle and those vehicles are capable of. So let's start with an empty transmission case. Okay, now that I've removed all the parts from the transmission case on this side, except for this one idler gear, we can put it together and see what is unique about the dual clutch assembly, and then what is unique about the electric motor being added to that, and then discuss the 3 overall modes of operation. So just like any other transaxle, we need a differential to allow the right front and left front tires to turn different speeds when you drive down the road and turn corners. This is a high performance differential. It is some sort of a limited slip or heavily preloaded differential to try to keep the wheels from slipping, and a lot of high performance cars have these limited slip differentials. This differential has a ring gear on it that has 68 teeth, and it is driven by a counter shaft. Just like any other manual transmission, there's a counter shaft that drives the ring gear. This counter shaft has a gear on the bottom of it, the equivalent of a pinion gear on a rear axle, and it has 19 teeth on it. And so this 19 tooth gear comes in and meshes with the ring gear. And now if we turn this counter shaft, we have 19 gear teeth driving 68 gear teeth. That gives us a final drive gear ratio of 3.579 to 1. So 3.579 rotations of our counter shaft to get 1 rotation of the tires. Now this counter shaft has some extra gears on it. So these other gears, so these 3 gears total, will allow power to be transferred in certain gears. So for example, on the back side over here, there is a shaft called the secondary shaft right here, and it has gears 4, 6, and 2 on it, and it will come in and mesh with the counter shaft only in gears 4, 6, and 2, or 2, 4, and 6, the even gears. And then there's another shaft right here called the main shaft, and the main shaft is what connects to the dual clutch assembly, and it comes in on this side of the counter gear and provides power to the counter gear in 1st, 3rd, 5th, and 7th gears. And so this same counter gear receives power from 2 different gear shafts, the main shaft and the secondary shaft. Now to make that happen, we have to get into the dual clutch and see how the dual clutch system works. So let me push this transaxle out of the way for a moment, the case. Now on this main shaft, if I take off all of the pieces except for these two, then we can finally get in and start looking at dual clutch. What dual clutch means, dual clutch operation. So this is the main input shaft, the main shaft that provides power from the engine on this side into this transaxle. And most manual transmissions over the years just had one input shaft. Most automatic transmissions just have one input shaft. But this one has an additional gear shaft. And notice it is a hollow shaft. Has a gear on the end of it, and it provides power in all the even gears, so 2, 4, and 6, where the main shaft only provides power in 1st, 2nd, 3rd, and 7th. And so we have two different input shafts that feed power to our two different gear stack-ups, the secondary shaft and the main shaft here. And then both of those provide power to the counter shaft at the appropriate time to send power to our differential to make the vehicle go down the road. So let's take a look at the dual clutches, the dual clutch operation. Okay, instead of having a torque converter like any other automatic transmission, this has a dual clutch assembly. And the dual clutch assembly, if you open it up, like I've done already, inside of it you will find two sets of multi-plate clutches. So this great big set of clutches, which is a set of steel plates, fiber plate, steel plate, fiber plate, alternating back and forth. There are 6 fiber plates in here. All of these clutch plates go down inside of here and are used to transfer power in all the odd gears. So these sit down inside of this housing. These clutches right here, which there are 6 more fiber plates, supply power in the even numbered gears, and they sit inside of this housing. So we have 2 housings, a large one and a small one, 2 sets of clutch discs, a large one and a smaller one, but the smaller one, the clutch discs are a little bit wider, so it evens out as far as how much torque they can handle. There are 2 clutch disc assemblies, clutch packs, that can be applied or released. And what that does is it will connect or disconnect one of these 2 shafts for the odd gears or the even gears to the engine or not. So when both clutch packs are released, there's no power from the engine into the transmission. But if we apply this great big clutch pack, then power from the engine will be connected to the main shaft right there. And if we apply the small clutch pack, then power from the engine will be connected to this hollow shaft right here for all of the even numbered gears. So if we put these 2 together, just like this, when I turn the large clutch pack housing, notice the center main shaft rotates, and that's the same as applying it and getting power from the engine. If I rotate the inner clutch housing here, it rotates the hollow input shaft to the transmission, and that sends power through the idler gear to our secondary shaft for all of the even numbered gears. So a dual clutch transmission really means that it has 2 clutches in it. And unlike the standard manual transmission single clutch disc that you might have with a manual transmission that's dry, or like the Ford Focus Getrag 6-speed transmission with the dual dry clutches, this assembly is always bathed in transmission fluid. The Honda DW-1 transmission fluid, and it allows for these to apply and release, a nice smooth apply and release, and to stay cool over time, which is a problem the dry dual clutches had to deal with. So we've got two input shafts, we've got two clutches in a big housing that almost looks like a torque converter, but it's not. It just has two different clutches on it. Those clutches are applied hydraulically. This dual clutch assembly is made by Luke out of Germany, I believe, but it has two bearings in it, release bearings, except they're actually apply bearings. And so there's one in the middle here that if I were to put compressed air or pressurized fluid to it, it would push it up and apply the small clutch pack. There's the larger one here on the outside that if I were to apply pressure to the inlet port, it would apply the large clutch pack back here and send power to the main shaft for all of the odd numbered gears. So on the back of this housing, we've got these two ports right here. One is for the small piston with the bearing on it. The other one's for the large one. I'm going to try to just gently push them forward. Let's see what happens. I don't want to pop them out too far. There we go. Looks like I popped it all the way out. That's all right. It just has a lip seal on it. But this piston, as you can see, can move forward. It can move up and squish those clutch plates and apply them. And that transfers power from the engine to the small clutch pack, which is our even numbered gears. And then if I hit power to, or hit hydraulic pressure to the larger one now, there we go, we pop it out, and you can see it comes out, just has a double lip seal. You can see there's just a cavity that it sits down in. And so this is a piston that moves up and down and applies the clutch pack. Well, it moves side to side and applies the clutch pack in the vehicle, but it has a bearing on the top of it to allow the apply plate for those clutches to rotate with the engine running. So just to wrap up on what dual clutch means, it physically means we have two sets of clutches in this housing here. A clutch or a set of clutch discs for the even gears, a clutch or a set of clutch discs for the odd gears, depending on the vehicle manufacturer, transmission manufacturer. All right, well on this one, it's a wet dual clutch transmission. They seem to be very reliable. I haven't read or heard about any issues with them. Okay, now that we've learned about the dual clutches themselves and the two different input shafts, let's take a look at how power is transferred into the even numbered gears. So we have our counter shaft right here. Let me just lift that up for a moment, because we are going to bring in the secondary shaft that has gears 4, 6, and 2. 4 right here, 6 right here, and 2 right here, and then we just have a power transfer gear down to the bottom here. But these gears are going to mesh with these gears, just like that. And then they're going to sit right down in the transaxle, just like that. So here's our counter shaft. Here are our even numbered gears. Okay, so once again, we have gears 4, 6, and 2 numbered right there. And if we want to transfer power into the transfer gear itself, then all we have to do is come in with some shift forks. It's like a Y piece of metal, and lift up on the synchronizer ring for 4th gear, and that's going to transfer power from this bottom gear into the top gear, into the counter gear, into the little final drive gear, into the final driven gear, to give us the gear ratio in 4th gear. We'll take a look at that here in a moment. So we can transfer with synchronizers. We still have synchronizers, the synchronizer rings, shift forks. As you can see here in this photo, there's a whole bunch of shift forks. The shift forks in this automatic transmission are computer controlled. And so, yes, this is a manual transmission, but it's automatically shifted. So you could call it an automatic transmission, but all dual clutch transmissions that I'm aware of are automatically shifted for you. And the big advantage there is that while you're in one gear, we can physically move the gear into the ready position on the other gear shaft and then just swap clutches, the even clutch for the odd clutch, and that actually shifts the transmission, not the physical moving of the sleeve, the synchronizer sleeve. And by the way, if you're not familiar, synchronizers, as the word implies, it synchronizes something. So we have gears. If you look at this shaft right here, if I keep the base gear from rotating, if I turn the final drive gear right here, here we go, notice that there are gears on this shaft here that rotate, and that's because those gears are tied to vehicle speed. But then this bottom gear right here and all the synchronizer hubs are tied to the engine. So we have engine speed versus vehicle speed controlling the rotational speed of these gears here. And in order to shift from one gear to the next, those speeds have to be synchronized. They have to be the same so that the synchronizer can easily move up and complete the shift. Now, how did power get over here to the secondary shaft? There's a gear right here called the reverse idler, as you can see, and it connects directly to the hollow input shaft from the small clutches in the dual clutch assembly. So now if I were to reach underneath here in the bell housing and rotate that hollow shaft, it transfers power to the reverse idler and then over here to the bottom of our secondary shaft. And then when the computer decides that you need second, fourth, or sixth gear, it will shift it automatically and transfer power into the transfer shaft and then into the final drive differential. So that's the even geared portion. So we have an input shaft just for the even gears in this secondary shaft. Now let's do the odd gears. Okay, I've got the main shaft put together. It has gears 5, 7, and 3. This is 5th, this is 7th, this is 3rd, this is reverse idler, and this is our even geared power input. And it also is going to mesh with the counter gear. So we'll put it down in with the counter gear. Just like that. Okay, now for power flow from the solid input shaft underneath the bell housing here. When I turn it, notice the upper shaft and the synchronizer sleeves and our reverse idler gear all rotate, but none of the other gears, the 5th, 7th, and 3rd gears, don't have any power to them until we move a synchronizer with a shift fork, computer controlled shift fork, to transfer power. And now this is 7th gear here where I've applied. We transfer power up the shaft into the 7th gear, into the counter gear, into the final drive gear, into the final driven gear, and our differential, and make the tires rotate. So now the tricky part about this whole thing is getting all 3 shafts in together. It's easy to put 2 of them in at the same time, but to get all 3 in at the same time without a special holding fixture that I don't even know exists. It probably does, but I don't think Acura or Honda even lets you or authorizes any diving into this transmission or any type of repairs on it. But that's what I like to do, is dig into things that nobody else does or you're not supposed to. So now let me put the even numbered gears, the secondary shaft, in with these all at the same time, and then we'll come back and add first gear, because notice up to this point we've talked about gears 4, 6, and 2 on the secondary shaft, and gears 5, 7, and 3 on the primary shaft. Where's first gear? Well, and where's reverse? First gear comes through and from the electric motor and a planetary gear set that we'll look at. So let me put this together, then we'll come back and look at the planetary gear set and the electric motor next. All right, now that I've got this transaxle, the 3 gear stacks all put together, the main shaft, the counter shaft, and the secondary shaft are all meshed and put in. And the hard part is you got to put all 3 in at once, which is a lot harder than it sounds. Now, I told you that we get first gear from the electric motor. So I've got the electric motor rotor right here, very strong permanent magnets. It's an internal permanent magnet rotor, and it has a set of splines right there in the center that connect to the input shaft, or the main shaft of the transaxle. So just like that. And if all we did was rotate the motor, it would turn that main odd numbered gears main shaft. But we need it to work in more than just the odd gears. We need it to work in the even gears as well. And so there's a planetary gear set involved, and it also gives us some additional gear reduction. So it's not just a 1-to-1 gear ratio here like you might think. So let's take a look at the planetary gear set that it connects to. Okay, so here's the planetary gear set that the electric motor drives the sun gear of. So every planetary gear set has a sun gear, a planet carrier, this piece that rotates right here, and then a ring gear or internal gear or annulus gear, depending on which book you look in. So let me get this put back together here. The ring gear has 111 teeth in it. The sun gear has 39, and the planet gears have 36. So if you do the math on the planetary gear set, we are holding the ring gear and preventing it from rotating in first gear, which means we turn the sun gear, which makes the planet carrier turn at a reduced speed. And the gear ratio is 3.8461. So it takes 3.8461 rotations of the electric motor and the main shaft to get 1 rotation of the planet carrier. And these splines right here connect right here. Here's our sun gear, just like that. So now let's go through 1st through 7th gears. For first gear, we use our planetary gear set, and we get our 3.846 to 1 gear reduction that turns 5th gear, and 5th gear has 42 teeth. It drives the 48 teeth of the counter gear, which drives the 19 teeth of the final drive gear, and the 68 teeth of the final driven gear. And if you do the math on that, the overall gear ratio from the main shaft to the counter shaft is 4.3959 to the final drive unit. And then you've got that additional 3.579 to 1 gear reduction. All right, so that's first gear. And that can be electric assisted. So now if I bring in the rotor, of our electric motor. It sits right up here on top and drives that main shaft and the sun gear of the Planetary gear set. So we can get first gear through electric motor operation, or we can get it through the odd numbered clutches on the main shaft, turning that same gear. So while we are in first gear, the computer has to predict which gear we will want to go into next. Chances are it's going to be second gear since we're in first. However, it could be neutral. We could go to park. There's a couple options there. We might want to go to reverse. So if we want to prepare to go to second gear, remember we only have power coming in on that main shaft through one of the two clutches in that dual clutch assembly. So now to go to second gear, while we're still in first, we pre-position the second gear sleeve. This bottom gear is second. So we come in with our shift fork, we shift down into second gear, but since there's no power to the secondary shaft here, we aren't actually in second. We're still in first. So actually, to shift from first gear to second gear, all you have to do is in that dual clutch assembly is release the large clutch and apply the small clutch. And you can adjust the timing of that to make it very quick. We can just go first, second, just like that, without having to synchronize gears or anything like that, because it's already been synchronized while you were in first gear. So when we apply the small clutch in the dual clutch pack, we apply power to this bottom gear right here, our hollow shaft. And that has 34 teeth that drive 54 teeth of the reverse idler, that drive 46 teeth at the bottom of our secondary gear shaft, and then second gear itself has 29 teeth that drive 59 teeth on our transfer gear. So if you do the math on all of those, not counting the final drive, then we get a second gear ratio of 2.754 to 1. So it's kind of a roundabout way to get over here to second gear, but that gives us second gear. All right, while we are in second gear, we can prepare to shift into third. So we're still in second gear with power on the small clutch pack in the dual clutch assembly, but now we can prepare to go to third gear. Well, third gear is this very bottom gear right here on the main shaft. So we'll come in with the shift forks, push down on that shift sleeve, and now to shift from second to third gear, we release the small clutch pack in the dual clutch assembly, apply the large clutch pack, and now power comes right up the main shaft to third gear, which has 29 teeth also, and it drives the same 59 teeth on the counter gear that second gear did, and that gives us a third gear ratio of 2.034 to 1. So an interesting thing I picked up here as I was exploring, both of these shafts, the main shaft and the secondary shaft, have the exact same number of gear teeth. For example, second and third gear both have 29 gear teeth. Sixth and seventh gear both have 53 gear teeth, and fifth and fourth gears both have 42 gear teeth. The difference there that sets them apart is that the secondary shaft back here has to go through the reverse idler, which gives it an additional gear reduction here from the hollow input shaft through the reverse idler and then to the secondary shaft. So identical numbers of teeth, which allows them to mesh with the same transfer gear. All right, so now we're in third. We can prepare to go to fourth. So over here on the even numbered gears, we can come out of third, and then fourth is this very top gear here. So now we'll come in with our shift fork, lift up, go into fourth gear, and now, once again, power comes in on our hollow input shaft with 34 teeth, driving the 54 teeth of the reverse idler, driving the 46 teeth of the secondary shaft, and then driving 42 teeth here in fourth gear to drive 48 teeth on the counter shaft. And so in fourth gear, we get a gear ratio of 1.5476 to 1. All right, so now we're in fourth gear. We can prepare to go to fifth gear, and we're just swapping which clutch, the even clutch or the odd clutch, to actually shift the gears. We just prepare before the shift takes place. So we are in fourth. Let's figure out how to go to fifth. Fifth is this very top gear right here. So we need to come out of third gear on the bottom. So we'll move this shift sleeve up, just like that. And then we'll move this shift sleeve up also into fifth gear, just like that. And now we swap from the even numbered clutch to the odd numbered clutch in the dual clutch assembly. Power comes right in on our main shaft and drives fifth gear, which has 42 teeth, driving 48 teeth of the counter gear. And that gives us a fifth gear ratio of 1.143 to 1. Now, while we are in fifth gear, we can prepare to go to sixth gear. So over here, sixth gear is this big one right here. So we will move from fourth, which is up to the top here, down to sixth. And then we swap which clutch we apply. We release the odd number clutch. We apply the even number clutch. We have power come in on our hollow shaft right here, the even numbered shaft, 34 teeth, driving 54 teeth. I know, I'm getting sick of it too. Driving 46 teeth. But now we drive 53 teeth in sixth gear, which drives a much smaller gear on the counter shaft here with only 33 teeth. And that gives us a gear ratio in sixth gear, an overdrive gear ratio of 0.8435 to 1. So now we're in overdrive territory. And this is a 7-speed transmission, so while we're in sixth gear, we can prepare to go to seventh. So back over here on the other side, we had the transmission in fifth gear with this shift sleeve. Seventh gear is this great big gear right here. So we just move our shift sleeve down to seventh gear. And now power comes in from our odd numbered clutch in the dual clutch pack into the main shaft, drives 53 teeth, just the same as the secondary one, which drives the 33 teeth on the counter shaft. And that gives us a seventh gear ratio of 0.623 to 1, which is a pretty good overdrive. Now, how does the electric motor fit into all of the gears above first? Well, it's already connected to the main shaft, so that it can help rotate in third, fifth, and seventh gears. And to go into, or to help supply power for the even gears, through the Planetary gear set, it actually drives fifth gear, the fifth gear teeth all of the time, even though the shift sleeve isn't engaged, which sends power to this upper gear on the counter shaft. So it doesn't matter if we're in the odd number gears or the even number gears, when this electric motor rotates, it supplies power in both odd and even numbered gears. All right, that's a that's a pretty involved transmission. The only gear left that we haven't discussed is reverse. And reverse, gotta watch that magnet. Reverse is right here. Okay, so there is a reverse synchronizer to go into reverse. When we want reverse, we simply move a shift fork up, and that changes the direction of our counter gear. And then I believe we apply third gear. However, there's somewhat of a mystery with this transmission and reverse as far as my abilities to figure this thing out. The published gear ratio for reverse on this transmission is 3.66 to 1. But I can't get 3.66 to 1. No matter what path I choose and what gear combination I pick to get reverse, I must be missing something, because I'm probably the one that's got it wrong here, but I cannot figure out how they get 3.66 in reverse. So if any of you know, let me know what mistake I'm making, but I can't figure that one out. All right, so we've got a 7-speed dual-clutch, wet dual-clutch transmission with an integrated electric motor that can help in all 4 gears. This motor can also act as a generator, because the vehicle that this is in, the Acura RLX and the MDX, but the Acura RLX has a rear electric motor set up with 2 electric motors, one for each rear wheel. And this can generate power as you're driving for a rear-wheel drive mode, which is one of the 3 modes of operation. There's another mode which is a front-wheel drive mode, and then there's an all-wheel drive mode where all the motors and the internal combustion engine are working together for maximum acceleration. You can see the stator here behind me, where the rotor sits and spins inside. There are all kinds of little cooling tubes and pipes to keep that rotor cool. There is a engine-driven oil pump that circulates fluid throughout this transaxle for cooling and for lubrication. Okay, as you've seen, this is a fairly complex transmission. All dual-clutch transmissions are. But the neat thing about it is the addition of this electric motor to give us extra power under certain situations. So there's an all-wheel drive, a super handling all-wheel drive version in the Acura RLX Sport Hybrid, and then a front-wheel drive version in the Acura MDX Sport Hybrid SUV. All right, well, that's been quite a lot of work, a lot of studying to try to figure this thing out, and it still kicked my butt with trying to figure out reverse. I just can't do it. I've wasted too much time trying to figure it out. So once again, let me know if you know. Otherwise, look forward to some more videos coming up. We've got several Tesla powertrains that we're going to be looking at very soon. So hope to see you then. Have a good day.